All right, let's jump right into it. It's kind of this fascinating biological paradox, right? The idea that a cell's most heroic and vital act might actually be orchestrating its very own destruction. We spend so much time focusing on how cells divide and grow to keep us healthy. But today, we're doing the exact opposite. We're looking at the highly regulated, perfectly coded mechanics of cellular death. So, to really get a grip on tissue health, we've got to start with a pretty fundamental question. What exactly does a biological system do with a cell that's, well, virally infected, severely irradiated, or just plain no longer needed? I mean, if that cell just bursts open or keeps living, it's a massive threat to the whole body. We need a clean, super efficient way to take out the trash. And that brings us to apoptosis. At its core, this is a highly regulated, energy-dependent process. We're not talking about some chaotic cellular murder here from an accidental injury. No, this is a meticulously organized, genetically programmed demolition protocol. It's literally an intrinsic suicide program designed to dismantle the cell from the inside out. And crucially, it does this without causing any significant inflammation to the surrounding neighborhood.
Now, this silent sacrifice, it's happening constantly in a healthy body. It is absolutely essential. Think about fetal development. Apoptosis actually sculpts our organs. Like, it's crazy to think about, but humans actually have webbed fingers and toes in the womb. It's apoptosis that meticulously carves that interdigital tissue away. It also handles hormone-dependent stuff, like endometrial shedding during a menstrual cycle. Plus, it's a huge player in our immune system, taking out self-reactive lymphocytes so we don't get autoimmune diseases, or simply shutting down an immune response once a bug is beaten.
But hey, apoptosis isn't just for routine maintenance. It steps up during pathological crises too, acting as this ultimate failsafe. Let's say a cell takes on severe DNA damage from radiation or certain drugs, or maybe it's just choking on an accumulation of misfolded proteins causing ER stress. Boom, apoptosis is triggered. It also breaks down cells that are irreversibly damaged by viral infections before those viruses can copy themselves and spread. It is literally damage control at its finest. All right, moving on to Section 1, the biochemical demolition crew. Let's meet the Caspases. So the real muscle behind this whole operation is a specific group of enzymes called Caspases, and they operate on a very strict chain of command, split right down the middle. On one side, you've got the initiator Caspases. Think caspase 8 and caspase 9. These are the bosses. They sound the alarm and get the ball rolling. On the other side, we have the executioner Caspases, like 3 and 6. Once the bosses give the green light, these executioners go straight to work, physically tearing down the cell's infrastructure by cleaving all sorts of crucial proteins.
Okay, so how do the initiators get the memo to start? Well, the most common route is the intrinsic pathway, otherwise known as the mitochondrial pathway. This is an internal alarm system triggered by cellular stress or DNA damage. When things go south, the cell's own mitochondria get leaky. The membrane literally becomes permeable and spills a crucial protein called cytochrome C right into the cytoplasm. And that leaked cytochrome C, that is the spark that activates initiator caspase 9, kicking off the whole executioner cascade.
Which brings us to this epic, constant molecular tug-of-war happening right at the edge of the mitochondria. See, the permeability of that membrane is fiercely guarded. In one corner, you have anti-apoptotic proteins, like BCL2 and BCLXL, doing everything they can to preserve the membrane and keep the cell alive. But fighting against them are the pro-apoptotic proteins, BAX and BAC, who are desperately trying to poke holes in it, release that cytochrome C, and trigger cell death. And overseeing this whole internal battleground is a famous tumor suppressor protein, P53. It is literally known as the guardian of the genome. P53 is constantly on patrol, looking for DNA damage. If it spots some, it'll first try to hit the brakes and fix it. But if the damage is just too far gone, P53 makes the tough executive decision. It commands the cell to die by cranking up the production of that pro-apoptotic BAX protein we just mentioned.
Now, the demolition order doesn't always come from an inside job. Sometimes it's an external self-destruct button. This is the extrinsic or death receptor pathway. Basically, external death receptors on the outside of the cell, like the FAST receptor, also known as CD95, will link up with FOS ligands on activated T lymphocytes. This external handshake forms a complex that directly activates initiator caspase 8. So, totally different starting line, same deadly outcome.
And whether it's the internal mitochondrial alarm or that external death handshake, all roads lead right here, the execution phase. Once executioner caspases, specifically caspase 3, take the wheel, they rip the cell apart fast. The cell literally shrinks, the cytoskeleton collapses, and the chromatin condenses into these dark, tight masses. Then endonucleases, which are basically the cell's molecular scissors, step in and chop the DNA into this super distinct, regular pattern called internucleosomal laddering. So now the cell is completely in pieces. But we can't just leave microscopic trash floating around, right? To prevent a toxic spill, these shrinking fragments pack themselves into neat little membrane-bound packages called apoptotic bodies. And here's the genius part. They display a specialized eat-me signal on their surface called phosphatidylserine. This acts like a giant beacon for local macrophages, which swoop in and essentially eat the apoptotic bodies, all without a single drop of the insides leaking out.
To really hammer home why this is such a masterpiece of biology, look at how it compares to the other major form of cell death, necrosis. Necrosis is messy. It's an accidental explosion where a damaged cell swells up, bursts open, and causes massive, damaging inflammation. Apoptosis? Completely programmed. The cell neatly shrinks, the membrane stays perfectly intact, and there is zero, literally zero tissue inflammation. It's the perfect, quiet exit.
Let's move on to Section 2, when the system fails. We'll look at the consequences of defective apoptosis.
Because it's an incredibly delicate balance, guys. If this highly regulated system underperforms, you get damaged, mutated cells that just keep living. They become essentially immortal, which leads straight to cancers and autoimmune diseases. On the flip side, if apoptosis is excessive, we start losing vital, healthy cells way too fast, and that is a huge factor in neurodegenerative disorders and ischemic injuries.
To give you a real-world example of how a defect causes disease, let's look at follicular lymphoma. In this specific cancer, a mutation triggers a massive overexpression of BCL2. Remember our mitochondrial tug-of-war? Well, with way too much anti-apoptotic BCL2 flooding the zone, the mitochondrial membrane becomes basically armor-plated. The demolition sequence gets permanently turned off, allowing the tumor cells to just survive and multiply because, well, they simply refuse to die. Before we wrap things up, let's quickly lock in these core concepts with a rapid revision of our major players. So, Caspases, those are your central demolition enzymes. Cytochrome C is the spark leaking from the mitochondria. BCL2 tries to stop the death while Bax and BAC push it forward. P53 is the ultimate DNA guardian calling the shots, and FOS is your external receptor. And the golden rule. Morphologically, apoptosis means cell shrinkage and absolutely no inflammation. So, what's the big takeaway from all this? It's how profoundly this exact mechanism impacts modern medicine. You know, a lot of contemporary anti-cancer drugs, chemotherapies, and radiation therapies, they don't just randomly poison cells. They actually work by inflicting highly specific cellular stress. And the whole goal is to artificially force those stubborn, resistant tumor cells right back into their natural apoptotic pathways. Which leaves us with a pretty fascinating final thought to chew on as we close out this explainer. We've just seen how apoptosis is this exquisite, incredibly necessary masterpiece of biology. So if our bodies already masterfully orchestrate this quiet cellular suicide to keep us alive and literally shape who we are, could the ultimate cure for diseases like cancer simply be unlocking and mastering this microscopic demolition code, basically teaching immortal cells how to die again?